Hello everyone, this is Jesse Crawford with New York Medical College, and this is a lecture on stratified 2x2 tables. This slide shows our first example of a stratified 2x2 table. Let's say you're interested in the relationship between some risk factor and a disease. For example, the risk factor could be something like smoking or eating unhealthy food, and the disease could be something like lung cancer or diabetes. The bottom table here shows a sample of 2,000 men and women broken down according to whether or not they've been exposed to the risk factor and whether or not they have the disease. Now, if we look at this bottom table, specifically if you look at the exposed group, you'll see that of the 1,000 people that were exposed to the risk factor, 290 of them got the disease. In other words, about 29% of the people who are exposed to the risk factor got the disease. On the other hand, if we look at the people in the bottom table who were not exposed to the risk factor, 460 of them got the disease, and that's 46%. So looking at the bottom table, 29% of those exposed to the risk factor got the disease, 46% of those not exposed to the risk factor got the disease. So based on this data in this table, it looks like being exposed to the risk factor actually prevents the disease. The problem with this is there could be another difference between the group of exposed people in this bottom table and the group of non-exposed people in the bottom table. And in this case, it's gender. It turns out that in this example, 90% of those exposed to the risk factor were male, and 90% of those not exposed to the risk factor were female. It also turns out that in this example, females are a lot more susceptible to this disease than males are. Because so many of the people in the exposed group are males, and because the males seem to be resistant to the disease, there's actually an illusion that exposure to the risk factor protects one from the disease. So, long story short, this is an example of a confounding variable. We're trying to compare two groups, the exposed group and the non-exposed group, but there's a difference other than exposure to the risk factor. There's a difference in gender. And gender is not only correlated with exposure to the risk factor, it's also correlated with whether or not someone gets the disease. So gender is a confounding variable in this problem. The relationship between gender and risk exposure and gender and the disease is creating the illusion that the relationship between exposure to the risk factor and the disease is different than it actually is. In order to overcome this problem, we need to break this bottom table up into a table for males only and a table for females only. Or you might say that we're breaking the data up into several layers, a layer for males and a layer for females. Now there's another word for layer that geologists use when they're talking about layers of the earth. It's the word stratum. A geologist will talk about the strata of the earth's soil. And by the same token, we're going to use the word strata to refer to these different layers of the data set. And that's why this is called a stratified table. So now that we've kind of given an overview of this situation, we're going to turn our attention to analyze the table for males only, the table for females only, and then we'll come back and analyze the table where males and females are combined into one data set. Okay, let's turn our attention to the table for males only. You'll see that this slide has several questions about this table, and the good news is we've discussed how to do all this stuff in the last lecture, so this should be a piece of cake. The first question says, what is the disease rate among males exposed to the risk factor? So we want to look in the exposed row. We see that there are 200 people with the disease, 900 total people. 200 divided by 900 is 0.222, so that's our answer to the first question. The second question asks the disease rate among males not exposed to the risk factor. So we'll look in the non-exposed row. We'll take 10 people with the disease, divide that by 100 people total, and we get 0.1. The third question is, what is the overall disease rate for males? So we need to look in the row with the total information. 210 people with the disease, 1,000 people total. 210 divided by 1,000 is 0.21. So now that we've looked at all these rates, the next two questions are involved with comparing these rates. First, we have to find the risk difference for males, exposed minus not exposed. So we simply take the disease rate among the males who were exposed and subtract the disease rate among males who were not exposed. So we take 0.222 minus 0.1 and get 0.122. And finally, we need to find the relative risk. In other words, we need to take the disease rate among males who were exposed and divide that by the disease rate among males who were not exposed. And so we just get 0.222 divided by 0.1, which is 2.22. The relative risk is the most important number on the entire slide because a relative risk of 2.22 tells us that for males, the probability of having the disease if one is exposed to the risk factor is 2.22 times as big as the probability of getting the disease if one is not exposed to the risk factor. So for males, exposure to this risk factor is associated with a higher chance of having the disease. Now let's turn our attention to the table for females only. All the questions on this slide are the same as the questions on the previous slide, so we're just going to use the same methods to approach these questions. To find the disease rate among females exposed to the risk factor, we'll just take 90 over 100, which is 0.9. Then the disease rate among females not exposed to the risk factor will be 450 over 900, which is 0.5. The overall disease rate for females is 540 over 1,000, or 0.54. Then the risk difference for females is P1 hat minus P2 hat, which is 0.9 minus 0.5, and that's equal to 0.4. And finally, the relative risk for females is P1 hat over P2 hat, which is 0.9 over 0.5, or 1.8. Again, the relative risk is the most important number. The relative risk of 1.8 says that for females, the probability of having the disease in the exposed group is 1.8 times as high as the probability of having the disease in the non-exposed group. So for both males and females, exposure to this risk factor is associated with a higher probability of having the disease. It's also worth noting that for every single disease rate computed on this slide, it's actually higher than the corresponding disease rate that we found for the males only table on the previous slide, which shows that for some biological reason or for some other reason that we're not aware of, females are more susceptible to this disease than males. Finally, we can repeat all these calculations for the table that contains both males and females. We actually performed a lot of these calculations on the first slide. The disease rate among males and females exposed to the risk factor was 29%. The disease rate among males and females not exposed was 46%. We can actually calculate an overall disease rate of about 37.5%, a risk difference of negative 17%. And then finally we get to, again, the most important number, the relative risk, which is going to be 0.29 divided by 0.46, or 0.63. Now, because the relative risk is less than 1, it means the probability of having the disease in the exposed group is actually less than the probability of having the disease in the non-exposed group. And this is what we're talking about on the first slide, that based on this data alone, there's the appearance that exposure to this risk factor is actually protecting someone from getting the disease. But as we've already discussed, this is really just the result of confounding, and we'll talk about this a little bit more on the next slide. Okay, now that we've analyzed each table separately, let's look at them all together and look at the big picture. This slide shows the table for males, females, and for males and females combined. And we also have the disease rates for exposed and non-exposed groups and relative risk rates for every single table. So the relative risk for males was 2.22, and the relative risk for females is 1.8, and then the relative risk if we combine both groups together was 0.63. The relative risks in blue are called strata-specific relative risks because they're specific to the strata that they correspond to. For example, the relative risk of 2.22 is specific to the stratum for males, and the relative risk of 1.8 is specific to the stratum for females. The relative risk in red of 0.63 that corresponds to the table where males and females are grouped together is called the crude relative risk. It's a crude measurement because it just groups both males and females together into one table, failing to take into account the importance of the gender variable, and it doesn't make necessary adjustments that should be made, which we'll discuss on the next slide. But before we go to the next slide, I'd like to talk a little bit more about the confounding that's taking place here. For males, the relative risk is 2.22. So males in the exposed group are 2.22 times as likely to get the disease as males in the non-exposed group. Similarly, for females, the relative risk is 1.8, and so females in the exposed group are 1.8 times as likely to have the disease than females in the non-exposed group. So for both males and females, exposure to this risk factor is associated with a higher chance of having the disease. This is something that we notice if we stratify the data by gender. But if we look at all the data in the bottom table that contains both males and females, as we said earlier, 29% of those exposed to the risk factor have the disease, and 46% of those not exposed to the risk factor have the disease. And so we get the illusion that exposure to this risk factor is actually going to have a protective influence and decrease the chance of getting the disease. Earlier I stated that the reason for this is because most of the people in the exposed group are males, most of the people in the non-exposed group are females. Males are relatively resilient to this disease, and females are relatively susceptible to this disease. And I just wanted to demonstrate that you can verify all of those statements with the data in the table. So for example, the bottom table shows that there were 1,000 people exposed to the risk factor. And among those 1,000 people, if we look in the male table, we can see that 900 of those were male. Similarly, 1,000 people were not exposed to the risk factor, and we can see in the female table that 900 people who were not exposed were female. So 90% of those exposed were male, 90% of those not exposed were female. Now what about the statements about resiliency and susceptibility to the disease? Well, that information comes from the disease rates. We can see the disease rates for males are 0.22 and 0.1, depending on whether that male was exposed or not exposed to the risk factor. And for females, the disease rates are 0.9 and 0.5, depending on exposure to the risk factor. So that shows that in this case, males are relatively resilient to the disease and females are more susceptible to the disease. So it's not the case that being exposed to the risk factor protects someone from the disease. It's simply the case that if someone was exposed to the risk factor, they're more likely to be male, and for this disease, males are less likely to have it than females. That's what's creating the illusion that exposure to the risk factor prevents the disease. The important lesson here is that confounding variables can really mess up your study. And there's a bunch of possible confounding variables. Gender isn't the only one. Things like age, income, geographic location, and really potentially any variable could be a confounding variable. That's why it's so important to understand the biological aspects of the problem that you're studying so that you can know what the potential confounding variables are and deal with them whenever possible. Ideally, you would like to just use randomized experiments to prevent confounding variables, but if you can't do that, we've presented one method here, which is stratification of your data, and another method would be to use some kind of a statistical model like a linear regression model. So to conclude this slide, the relative risks that we really want to pay attention to are the strata-specific relative risks. Both of those are greater than 1, which shows that there's really an increase in the chance of having the disease when someone is exposed to the risk factor. The crude relative risk is problematic and misleading. It's less than 1, and it gives the illusion that exposure to the risk factor decreases the chance of having the disease. So earlier we talked about the possibility of making some kind of an adjustment to the crude relative risk, and that's what we're going to do on the next slide. On the last slide, we talked about the difference between strata-specific relative risks and the crude relative risk. We also talked about how the strata-specific relative risks do a better job of summarizing the relationship between the risk factor and the disease than the crude relative risk, and that the crude relative risk probably needs to be modified in some way to provide a better idea of what's going on. And that's the purpose of the Mantel-Hansel summary relative risk. I'm not going to go into too much detail about this statistic, but suffice it to say, it's an attempt to correct the crude relative risk so that you can get an overall summary of what the relative risk is that takes the confounding into account. You'll notice that in this problem, the Mantel-Hansel relative risk is 1.87, which is more consistent with what we were saying on the previous slide, that exposure to the risk factor does increase the probability of getting the disease. You can also see that 1.87 is between 1.8 and 2.22, which were the strata-specific relative risks, and those were better indications of the true relationship between the risk factor and the disease anyway. This raises the concept of positive confounding and negative confounding. Positive confounding is when the crude relative risk is greater than the Mantel-Hansel relative risk, and negative confounding is when the crude relative risk is less than the Mantel-Hansel relative risk. So in this example, gender is a negative confounder because the crude relative risk is less than the Mantel-Hansel relative risk. One way to look at this would be to say that the Mantel-Hansel relative risk gives you an accurate picture of what's going on, and then confounding either has a positive impact on that, in which case it increases that value and the crude relative risk gets bigger, or the confounding has a negative impact on that Mantel-Hansel relative risk, which makes it smaller so that the crude relative risk is smaller. So at this point, we've actually covered most of the important concepts for stratified 2x2 tables. The only thing that remains to do is to go back through these tables and discuss them from the perspective of odds as opposed to disease rates. So as a quick reminder, odds is what you get when you divide the number of people with the disease by the number of people without the disease. So the odds for males exposed to the risk factor would be 200 divided by 700, which is 0.286. And then for those not exposed, it would be 10 divided by 90, which is 0.11. For the overall disease odds, we would take 210 divided by 790 and get 0.266. And then we have an odds ratio, which we simply obtain by taking the odds in the exposed group divided by the odds in the non-exposed group. So we have 0.286 over 0.11, which is 2.57. Okay, now we're just going to repeat these calculations for the females only table. In the exposed group, the odds were 90 over 10, which is 9. In the non-exposed group, it's 450 over 450, which is 1. The overall disease odds are 540 over 460, which is 1.17. And the odds ratio is 9 over 1, which is 9. Finally, we can look at the table that combined both males and females. In the exposed group, we have odds of 290 over 710, which is 0.408. In the non-exposed group, we have 460 over 540, which is 0.852. Then our overall disease odds are 750 over 1250, which is 0.6. And finally, we have an odds ratio of 0.479. Now we can see the same patterns for the odds ratios that we saw for the relative risks. The strata-specific odds ratios are 2.57 and 9. Both of these numbers are bigger than 1, showing that the odds of obtaining the disease in the exposed group are higher than the odds of having the disease in the non-exposed group. The crude's odds ratio was 0.479, it's less than 1, and it seems to indicate that the odds of getting the disease in the exposed group are less than the odds of getting the disease in the non-exposed group. However, we know that a crude's odds ratio is going to be just as misleading as a crude relative risk, and so there is a mental Hansel technique for adjusting the odds ratio as well. The mental Hansel summary odds ratio in this case would be 5.09, which is more in line with what we got with the strata-specific odds ratios. Finally, we can approach the concept of positive confounding and negative confounding from the perspective of odds ratios instead of relative risks. The pattern is the same. If the crude odds ratio is greater than the mental Hansel odds ratio, then we have positive confounding. If the crude odds ratio is less than the mental Hansel odds ratio, then we have negative confounding. So once again that we see that gender is a negative confounder for this example because the crude odds ratio is less than the mental Hansel odds ratio. Well guys, that just about wraps up our lecture on stratified 2x2 tables, and as always I'd like to encourage you to just let me know if you have any questions about anything. If you have any questions about the lecture or about the homework problems, please feel free to send me a private message or just feel free to post a question in the forums.